For almost 100 years, there's been this one massive question that sits at the very heart of cosmology. It's the foundation for pretty much everything we think we know about the universe. But what if new evidence is telling us it's time to take another look?
And that question is this: why is our universe expanding? See, back in the 1920s, Edwin Hubble noticed that all the distant galaxies seem to be rushing away from us. And the further away they are, the faster they're going. This discovery, called cosmic redshift, gave birth to the entire theory of an expanding universe and, the Big Bang. But what if that's not what's happening at all? What if that foundational assumption was just a misinterpretation of the data they had at the time? It's a pretty wild thought, but a new theory is suggesting that a universe that isn't expanding might actually be a much better fit for the evidence we have today.
Okay, so to really get this new idea, we first have to talk about the standard model and some of the really strange puzzles it's left us with.
Yeah, the thing is, the current model, it's got some real problems. For one, there's this thing called the Hubble tension, where we get different answers for the expansion rate depending on how we measure it, which is weird. And to make all the math work, the model needs these two mysterious things called dark matter and dark energy, stuff we have literally never seen or detected. And maybe the weirdest part? The expansion we measure looks surprisingly constant, which is really not what the theory says it should look like.
So, how did we even get here? I mean, to question an idea that's been around for a century, you've got to go back to the beginning, back to the world it was born into. Think about it. Back in the 1920s, when Hubble first suggested that space itself was expanding, the whole scientific world had a different view. Most people, even Einstein at first, figured the universe was just eternal, static. And the idea that gravity wasn't instantaneous, that it actually had a travel speed, that was pure theory. So Hubble saw this redshift, and he went with the only explanation that made sense with the science of his time, a Doppler effect. The galaxies must be physically moving away from us. But then, something huge happened. A new piece of the puzzle dropped into place just a few years ago that completely changes how we should look at Hubble's original observation. And this is where it gets really interesting, because we have to talk about Einstein's equivalence principle. It's a cornerstone of relativity, and it basically says there are two equally valid reasons why you might see a redshift in light. One is the Doppler effect. The source is physically moving away. But the other reason is that the light traveled through a gravitational field that was changing. According to Einstein's own math, you can't tell the difference. Both are equally possible.
Okay, I want you to burn this year into your brain, 2017, because this is the moment when a question that had been pure theory for 100 years finally got a real, solid, experimental answer.
So in 2017, the LIGO experiment made this incredible detection of gravitational waves. And for the first time ever, we had rock-solid proof that gravity isn't instant. It travels. It has a speed limit, the speed of light. And that, right there, is the game changer. It's the one piece of information that Hubble and Einstein just didn't have. And that one fact, that gravity has a speed limit, well, it blew the doors wide open for a whole new way of thinking about the cosmos, one that doesn't need expansion at all. So this new idea is called dilation flooding. The core concept is pretty wild. Since the universe had a beginning, and since gravity takes time to get from one place to another, we are constantly, right now, feeling the gravitational pull of more and more distant stuff for the very first time. It's like we're in a rising tide, a flood of background gravity that's always getting stronger. And what happens when gravity gets stronger? Time slows down. It's called time dilation. Okay, let's picture how this works. Right after the universe began, things were pretty localized. The gravitational influence from, say, a clump of matter over here hadn't had time to travel very far yet. These little spheres of influence are all separate. Okay, now let's fast forward a bit. As time marches on, those waves of gravity keep spreading out at the speed of light, and you can see they start to overlap. The background gravitational field, which is really just another way of talking about time dilation, starts to go up everywhere. And if we jump all the way to today, our little corner of the universe is just, well, it's flooded. It's filled with the combined gravitational influence of everything we can see. So any light that's been traveling for billions of years to get to us has passed through a universe where time itself was gradually slowing down. And that journey changes the light. It drains its energy, making it look redshifted to us. So the big question is, does this new idea actually explain what Hubble saw? How does it stack up against the original mystery?
See, the weird thing about the standard expansion model is that its equations predict these really complex, curvy lines for how redshift should behave over distance. But for 100 years, what we've actually measured is an almost perfect straight line. The standard model has to kind of wave its hands and say, oh, it's just a cosmic coincidence. We happen to live at the one special time when the curve looks flat.
But dilation flooding? It doesn't need a coincidence. It doesn't need us to be in a special place or time. It predicts a perfectly straight line right out of the box.
Okay, so why a straight line? It's actually incredibly elegant. Picture the universe as a bunch of nested spheres, like Russian dolls, with us at the very center. Now, the gravity from any single star gets weaker the farther away it is, right? That's the inverse square law. But the farther away a shell is, the bigger it is, so it has way more stars in it. And it turns out those two effects, the weakening gravity and the growing number of stars, cancel each other out perfectly. So every single shell, no matter how far away, adds the exact same amount to the flood. It's just a simple, constant, straight line effect.
All right, let's just lay it all out, side by side. The old idea, Hubble flow, says redshift happens because space is stretching, which needs a mysterious dark energy to power it, and it can't really explain why we see a straight line. The new idea, dilation flooding, says redshift happens because of rising time dilation. It only uses physics we already know is true, and a straight line is exactly what it predicts.
So if this is right, the implications are just huge. It forces us to completely rethink the very nature of our cosmos.
So what's the big takeaway here? Why should you care? Well, first off, this could solve one of the biggest mysteries in science, using only the physics we can actually prove. It means we might not need to invent things like dark energy. And it perfectly matches the actual data we've been collecting for a century. More than anything, it's just a fantastic reminder that in science, nothing is ever truly settled for good. And this all kind of leads to a really beautiful idea. You know, the ultimate goal in physics is to find rules that work everywhere, at every scale, without needing any special exceptions. And that's what's so compelling about dilation flooding. It's an attempt to apply one simple rule, gravity, to the entire universe and see if it just works.
And that's really the thought I want to leave you with. We just saw how a single new discovery, the fact that gravity has a speed, could completely reframe 100 years of thinking. So what other things that we accept as truth today are just waiting for one new piece of evidence to come along and make us see everything in a totally different light? It's a good reason to always stay curious.